So let's get to the webinar topics. Although we do a lot of different things in many different industries, we've found that the marine industry is probably the single biggest industry that has some of the largest needs and the biggest payback for using laser scanning. And so today we're going to be talking about 3D facility configuration models. This is a really growing field. We're also going to discuss 3D modeling of ship hull and interiors for CFD, Computational Fluid Dynamics, and stability analysis. We have examples of this. Ship hull as-builts for docking plans, very cost-effective to use laser scanning for this process. And then the one that really got us into the industry, our background was refining. We did a lot of piping jobs, and it just so happened that one of the constructors for one of the piping jobs ended up taking on a large piping retrofit for a large ship, and he said, "Hey, can you guys come out and scan this?" And of course we said we could, and the huge benefits to his project were just instantaneously appreciated. So, and then finally we mentioned our in-house software. We're actually getting ready to go out and offer to clients. Cohera 3D is our software side of our company, and it's specifically going to be a little example of how we apply that to piping systems. So let's get going to kind of our workflow. Well, the new scanners have allowed scanning without the tremendous surveying requirements that used to be just a standard part of the industry. So we now scan for targetless registration in almost every case. We do often use targets to tie the scan model to a client's reference coordinates. So in the ship, that would be frame numbers, the center line of the ship, whatever the client is using for their facility. If it's a facility, they might have coordinates that have a certain 0, and all we need to tie this into their coordinate system is something in our scan data that has a coordinate that we put in there, and then everything gets shifted and rotated to match that, elevations, everything. So we then pre-align scans in Ferrocene. This is the program that comes with the Ferro scanner, and their alignments, Ferro's registration is improving, but we've still found that we do a little bit better when we finalize the registration in Leica Cyclone. And this is a cloud-to-cloud registration, and so people will talk often about targets, and you may set up a few targets that are seen in multiple scans, and then when they do target registration, it actually looks to the center of those targets, it locates that, and then it uses that to line the scans up. What we've found is with Leica Cyclone, the cloud-to-cloud registration is effectively using 1 million targets or 500,000 targets, whatever number of points that overlap between these scans. That's effectively what Cyclone is using. So you'll see a lot of push in the industry to move to cloud-to-cloud registration. At this point, we still see Cyclone as being the best one in that on a production scale. And a lot of people have that program, so they can buy a Ferro scanner and still take advantage of the software they already own. And we've just had tremendous results, and the improvement in the scan data and the noise of the scan data from the newer model scanners, Ferro scanners, has been a big part of that registration process, getting so clean and so streamlined. So we then post-process scans in what we call our proprietary software. This includes filtering, which often there's noise, reflections, mixed pixels, edge filter problems, and we've created a few filters that help clean up the data further while still maintaining the data you need to do your design. And then you'll see as we go through our presentation, a big part of our workflow is we isolate the data out into key components, and those actually become layers that we can use in our modeling functions. So, and then we model in CAD. Pretty much everything that needs to get done is done in a CAD program of some sort, and there's so much commonality between them that pretty much any mainstream CAD program can take in the isolated groups that we create. So, and I'll talk a little bit further. There is huge improvements being made in CAD programs to be able to handle larger data sets, but they still have a limit. And so I think the isolations that we provide still provide good functionality and performance and efficiency in the CAD models. So you see there, Ship Constructor is an it runs on an AutoCAD platform. Plant 3D is AutoCAD, and of course AutoCAD. Rhino has been very, it's just used throughout the industry for freeform holes and that type of thing. And then SolidWorks, it just depends what our client is using. And then finally, across the board, we use Navisworks models. Visualization, we can create a Navisworks Freedom file, and even if our client doesn't spend the money for Navisworks, they can still get these files where they can go through the 3D model and look at different things and even take measurements. And it's a free viewer provided by Autodesk. So let's start with a facility configuration model. This is actually a dry dock, and this is all scan data. So as you can see, we've isolated out different items that can be then brought into AutoCAD or any CAD program and modeled individually. So typically from here, we would, once again, our process is, and the purpose is, you got accurate facility point cloud models. So these are very useful for visualization of staged production lines, so where you put everything as you're bringing something through your facility, simulating crane reaches, throughput modeling, so where do you get stuff at what point in your process on the facility, in the facility layout, staging of materials. And then a big one is you've got these older shipyards and that have clearances, and now they're trying to build larger ships in them. Well, what happens if the facility actually impinges on something you expected to use to make your production very efficient, like an automated welding machine? Well, you can do this all in advance in a virtual world before you ever bring the expensive, hard-to-move items into it. So the method is just to scan the existing facilities. It's usually not... Existing facilities are usually fairly open, and so you can scan them pretty quickly, align it to facility coordinates, you isolate the various structures, model what you need to model, and then you can bring the models into production simulation programs, such as knowledge-based systems, KBSI's WorkSim. And this KBSI is really focused on the marine industry, and for those who will be at SNAME the last few years, KBSI and Summit have had adjoining booths, in the same area. And so if you are going to make it to SNAME this year, we're going to be booths 507 and 508 for KBSI, and you can actually see a working WorkSim example.
Hey, Darren?
Yes?
We've got a question here from Harriet Kinney. She wants to know, how much will this technology cost or save the marine industry in reference to ship cleaning and hull fouling?
The biggest value is if you already have the data. So, and I'll talk about that when I get to the docking plan, but I'll discuss it real quickly. The biggest problem with determining the cost when you get into a dry dock of what it's going to be is what's the true square footage. And so if you've already scanned a ship and you already know what that is, then you as the owner, you would give the dry dock or the facilities the number, and then they would say, okay, it's going to be this amount. What often happens is you end up in a T&M type thing, and it just grows and grows and grows. So that's the biggest benefit we've seen. And just as an additional thing, and even a bigger impact, is how much paint are you going to need? So you'll see this is a big deal. And when people are trying to plan what it's going to take to actually do something in my facility. So we'll talk a little bit more, I think, as we go through this and get through the different issues dealing with the surface, the hull, H-U-L-L, of ships. I think it'll become apparent how you guys could use that in your own planning purposes. Does that make sense? So with that, I've got a little video here and this is that dry dock we were just looking at. And you saw we noted that is the blob. It's a big white, you can't see anything. When you isolate it down into these different components, now you can start to visualize what it is you actually have and where different things are in relationship to the things you care about. So here we're pointing out just, you got your tower, you got the controls for the dry dock, the railing, stairs, get there. You'll notice that all that pink stuff is just kind of garbage. And so that can be taken out. So now we want the deck. So here you have a flat surface, really easy to model a flat surface. And so what happens is you give out these different pieces, and they pull them into CAD, and you model them. And so that's kind of what you're seeing here. You're seeing things built one on top of the other, and we're going to go from isolated components to modeled components, and then we'll pull the scan data out.
Hey, Daryl, sorry to interrupt. We just have another question here. How long does it take to isolate each of these elements?
The total, it's hard to say for each element. For example, flat planes are pretty easy, but I think the total isolating time for this specific example was about 6 hours, 4 to 6 hours. This one's pretty simple. It's easier than a piping system, so I would say it was no more than 4 hours on this. So and that's because of, like I said, the simplicity of it. Get into a piping system, it's a little more, but we'll also show an example in the piping of just how valuable isolations are. So there's the dunnage, and dunnage modeled. So there's your docking plan. Well, no, the docking plan will be coming here shortly, because when this was scanned, there was a ship there. And that's, we were there primarily for the facility, but and the ship, but it would have been very simple now to confirm the docking plan. So the next time that ship was going to be brought into the dock, the docking plan, the docking plans we've done so far, or the scans we've done for docking plans, the ship's owner is the one who wanted that, so that they could give a docking plan to a future dry dock case. So, and we'll talk about that a little bit further. So here you see the white is unisolated, the isolated, and then the cloud, or excuse me, the model. Now, you still need models in many cases, just because the sheer volume, the sheer size of these scan files it's like a multi-megapixel picture. It takes a lot of memory, and it slows down CAD systems quite a bit. So on this particular one, we were asked about scanning and using scan data on a propeller. So we did an example, a model of the propeller, and you can actually use that to determine if a propeller is in balance. So here you can see the tolerances, if a welding machine is going to fit down there. Not as big a deal in the dry dock as it would be if you envision this being an enclosed shelter that had trusses and columns that were coming in and impinging on it, where you might be able to get equipment through that. So now we're doing something tricky. We took that ship that was scanned in a dry dock in Texas, and we've now moved it to a dry dock down in Panama. It's all scan data. We took the scan data that was isolated out for the ship, and we moved that, and located it in the dry dock. Now, with this, you can see that all of this is scan data, but you can clearly see the tracks. So here's the tracks that the crane runs on, and that gives you all the throws, all the locations, all the movements that can occur with these cranes, and give you your crane reaches and such. And if your car was parked there, you can see the car. This is a little boat that was off to the side. It shows up there. We didn't take it out just because we thought it was cool. So that brings us back to our discussion of KBSI's WorkSim program. Here is a screenshot from WorkSim, and it's been annotated to show how it can actually be used for your business. Got a dry dock model, provides visual reference for crane locations. Vessel clearances for work areas can be validated before docking. Interferences become visually obvious And then crane movement. There's a lot of programs out there that can you actually have your item, your crane, and you can move it through the yard, attach it to the rails in this case, and get it to where it needs to be, and just confirm. Basically, a virtual run through the entire facility before you ever even start. And with that helps you define your schedule, your requirements, process steps with durations and resource assignments, resource definitions including dry docks and cranes, and all of that. And this is how the new industry is really getting more efficient and being able to do more with the existing facilities. So, any questions you might have as we finish up with 3D facility configuration models? So, okay, we will move on to another area that is growing significantly for a lot of reasons, but I will say the biggest one is fuel costs. For me, fuel costs are not too terrible because we work in refineries as well, and we work in crude production. But for shipping companies, the cost of fuel and optimizing is one of the big requirements or one of the big justifications for computational fluid dynamics and hydrodynamics. So you'll see at SNAME and Workboat, you'll usually see 5 to 10 companies who are selling their wares for their computational fluid dynamics programs, and the reason why they can do that is because it's worth a lot of it has high value in the industry.
Actually, Daryl, I'm sorry. We do have one question.
Okay.
About the 3D modeling.
Okay.
Let me just hang on. I'm just waiting for Joe to write the rest of the question. Or do you think it would be better to come back to that?
That's okay. We can jump in. We're still kind of in that same area, and it's fresh. So we'll. I'll just finish going through this slide, and then you can ask the question. So the issue, what's growing in the industry, is the need for good models, valid models of the hull of these vessels, and because they're used in many different ways. So, and one of the last ones you see here is modification or repair to a hull. And I'll give you an example of one. There's been a lot of work done recently on vessels that were, short, and they decided they wanted to lengthen them. And so what they do is they cut them right down the middle, or some reasonable spot, and they drop in an extension, or not an extension, but just a place in the middle, and they make it 20-30% longer. Well, to do that, you either need to brute force the metal into place, or you need to scan. There's really no other way to measure it such that it will really line up properly. If you do it the brute force way, everything has to be custom fit, both ends, at the point of insertion. However, if you scan it and you model it properly, you can actually roll it and bend it and shape it and prefabricate it so that they come together, just like they're doing for new construction. So scanning has a tremendous value in that respect. So you got the question there?
I'm not yet. Still waiting on it.
Okay, we'll keep going. So there's a little bit it's a little bit different when you're getting into this type of modeling, because these surfaces are freeform for all practical purposes. So there's a lot more precision and mathematical fit requirements for this than there is per se in a perfectly round cylinder or the flat parts of a facility. So of course we scan, we register, just like we do for the others. We then prepare the surface, and we found that when you're trying to fit a hole, you really need to get just the hole. You want to get all the other pieces that, the keel coolers and all the other things that aren't part of the hole, you want them out of there. If you leave them in the scan data before you fit that surface, you have a lot of problems you have to clean up in the surface fitting. So we filter and clean up the data, the invalid data. That doesn't mean we get rid of the keel cores. You end up having to put those back if they're of any significance, because they do affect the hydrodynamics. And then you remove the non-hole data and the mathematical fit of the prepared scan data, and then refinements to create final surfaces. And these are often done in programs like Rhino. So NURB surfaces, that's basically Rhino is that. Hole curves, interior surfaces, decks, compartments, bulkheads, penetrations, large equipment. Those last, the interior surfaces, that's more normal, that's more common, because they're usually flat and something relatively easy to model. And we don't really care too much about the exact shape, so you really model it to whatever you need. The hole you care about, because that surface shape is what impacts the hydrodynamics. The interior, you mostly want it to be roughly in the right location and roughly the right shape and size so that it can get the right weight for the stability analysis. So, you have that question?
Yes, I do, Joe. It's from Joe. So he says, okay, so as I understand the service, you could then take a snapshot of, for example, a pump room, and then create the picture and decide how and if possible someone could add in a ballast water treatment system.
Yeah, in fact, I'll do this more when we get to it, but this is Navisworks. This is all scan data, so I'm trying to move slow because when you're doing a live program, this is a ballast water treatment facility, small one, or module, and in this case, it was kind of coming from the vendors, their module set, but in reality, you don't usually have this much space in a ship. So
that's great. Joe said that's exactly what he's talking about.
Yeah, so we'll talk more about this when we get to the piping system. But yeah, this is to me what is really it's huge in the industry, because not just because this is now an environmental requirement, but because there's a lot of things that ships would like to put in. Like we did a job, and I'll give an example. Here's a pump, but it's a single source pump. It does not have a spare pump, and so I'll talk further about that when we get to that point. So let's get back and keep the questions coming. I don't care if the questions are in order, as long as we can keep in track. We're answering things that are real world questions you guys have. That's the purpose of this. Someplace that you can apply this technology to save money and get jobs done better. So with that said, this is a ship that had a significant...
Oh, we have another question there, Darryl.
Okay.
This is from John. How are you defining the center line on older vessels in particular that are not perfectly symmetrical port starboard?
Okay.
There's a little bit related to this. How are you setting up baseline and identifying internal structure to align things on standard frame locations?
Okay, so I'll answer that one, but I'm going to let Norm answer the first one, because we did the Glomar Explorer. For those of you who know history of ships, was a ship that Howard Hughes built to recover a Russian submarine that sunk. It was built, fast and was thrown together, and so the pipes were not square. And so, actually, Norm, why don't you go ahead and explain? What we did is, the client needed something that would give them a reference, and so.
It's quite possible there's a beam that's down the center that we can line to, and if it provides a symmetric geometry, then we can use that to compare to. Also, it also depends if you can actually see the inside of the hole, and then we can compare the symmetry between the two sides. And if there are wing walls or whatever, we may have to work with drawings to help facilitate understanding that. And I think this is also a part where the owner needs to play a role from the standpoint of what's important to them.
Yeah.
So if the rule of thumb to keep in mind here is, if you can see it, we can scan it, whether it's in a compartment or whatever, and we can connect it to the rest of the scan data. But with the cases we've had, we've been able to find a way to do it. Sometimes there's a mix of different methods.
Okay, yeah. So then I'll answer the other one in terms of how you tie it into the frame. What we find, the scan data is especially for older vessels, way more precise than even the ability to construct it in the olden days and locate their frames. So what we do is we have the client actually identify, for example, a bulkhead and say this bulkhead is frame 95. And from then on, all the other frames are referenced to that. We call that one right, and then we let them know where the other ones are compared to it in terms of the drawing. So even though they may show a 3-foot spacing frame to frame to frame to frame, there may be a 35-inch spacing and then a 37-inch frame spacing, and it might have even occurred at frame 95 bulkhead. And so we give them the option to tell us that and a center line, and then from there we let the data define where everything else is. And so as long as they understand that this new technology on an older ship is better than what they had to build it, or what they typically use to build it, we're usually pretty good. They understand that you've got a certain amount of leeway. There was one other piece. About symmetry.
I'm sorry, go ahead.
About symmetry. We had an inquiry. We actually didn't do this job, but they wanted to evaluate it for hydrodynamics, and they said, well, we're fine just assuming it's symmetrical. I thought, okay, that's interesting, because it was a really old vessel. And so what I told them is, if that's what you want, you really only want us to scan one half, actually just a quarter of this, just the front quarter. I says, then you have to locate a target on the keel. What you determine is the exact center line, and you need to do that in 2 places. Since they didn't want to pay for the whole thing to be scanned, we weren't going to be able to get along, enough length to give a good center line. So that was going to be their job to do. It ended up not going through. I'm not sure the vessel was so old that it was able to justify all, not just our efforts, because ours was only going to be a few $1,000s of the whole thing. I think they canned the whole project because they probably only had another few years of vessel life. So does that answer your question?
Yeah, there was actually a follow-up which I didn't see before. It's same from John as well. Are you applying tape or magnets to the exterior of the hull at known locations of decks, bulkheads, and frames?
No, we haven't yet. What we've talked with certain clients about is doing that so they have the equivalent of a monument system, but it wouldn't be something that would be temporary. We would suggest that they put in a monument that becomes a standard, just like surveyors' monuments on land. And so from then on, that's a known place, and then it would show up in your scan data, and it would define where you are relative to the equivalent of plant coordinates, but the coordinates that they care about for the ship.
And we have one more question from Bill. He wants to know, how accurate is the scan? 0.01 millimeters, or how long does it take?
Okay, not 0.01 millimeters. I do have an example of that, but no, the focus scanner is classified as a 1 millimeter machine over 25 feet. We found it does better, but understand too that you also are registering scans to scans to scans. So what we pretty consistently say, if the surfaces are good, which a ship is almost always good, we've had problems in areas where it's really shiny, like brand new factories. We did a job at Los Alamos National Laboratories where there's a lot of shiny stuff. Companies like Intel have a lot of shiny stainless around. Those shiny surfaces aren't as easy, but we've never found a problem with too much shiny on a ship. They're always pretty dirty, and so we easily can get a 1/4 inch over 50 feet.
Okay, and then John asked again. He said we have used companies before, and their machines have had trouble seeing dark-colored and/or wet hulls when scanning. Do you have similar issues?
Yeah. Let me wait till we get to our docking plan, and I'll talk about that. We do have similar issues. We've developed a few workarounds, and when I talk about filtering data, one of the things is reflectivity is a big deal. And so yeah, let's get through this one, and then when I get to the docking plan, which is next, we'll actually have an example. That was in the docking plan one. So here is that was the whole vessel you saw. Now it's just the hull. So remember we talked about pulling everything off, so you have just what you care about for modeling it and getting the freeform curves or the curves for the freeform shape. So now you have those curves, and notice it's only the part of the vessel that's going to be actually touching the water, and is what's impacting the hydrodynamics. So, but next you still need to model. Now we will. Here's where the client, depending on where the client's capabilities are. Typically, if a client's asking us for this, they have a design firm that can do the interior stuff. And so, even though on this one we did everything, we're happy to focus on the parts that people really have trouble with, and give some of the easier stuff back to the client to work on. So in this case, although we modeled this, what we did is we gave the model to the client and let them determine the weights of those surfaces. Because as I mentioned, you can't determine, you can locate where things are in the scan, but I can't sit there and tell you that the scan, what the thickness of each of these members is, and that's what defines the weight. So I can't tell you what it is, and I can't tell you how thick it is, but I can tell you where it is. So in this case, we modeled all the internal features of this vessel. This vessel had so many revisions done to it that it became basically top heavy, and it needed stability analysis just to make sure that it would work well. So that, and this is kind of a little plug for Autodesk. Autodesk has done so many great things to also make things pleasant to look at. And this is just a rendering program called Showcase. And so that model you saw before, which was the meat and potatoes of it, this is the show and tell of it. So if you guys need to make presentations and you're using Autodesk products, this is Showcase, and is a nice one to use. So here is this is a hull. This is a ship that needed a stability analysis, and it is obviously not ready to float, but it was ready to be scanned. So we scanned it, and here is here is that hull. And once again, all we scanned was that hull. We didn't go into it because the owner, they already had a pretty good idea of what they were fine with the putting in the weights of the interior parts. So here is it after it was put out in the water, and they were pretty pleased with it, and then sent us a picture, and I think it was a win-win for everybody. So real quick, I don't want to run out of time, but I just can't pass this up. If anybody is going to be going to SNAME this year, swing by our booth. But we were asked. There's going to be a 4-panelist discussion on laser scanning applied specifically to computational fluid dynamics. And so they thought it'd be cool if we took a footy boat. So if you're familiar with SNAME and the footy regatta, this is actually the president of SNAME's footy boat. So he got it to me, and we scanned it. Well, we scanned it with our big scanner, and that just didn't work because the scan data is not made to scan something 1 foot long. That's a point, as somebody mentioned, a 0.01 millimeter machine. So what Faro did, they were very, very good to us. Faro is great to work with. They're so accommodating. We got together with their Faro arm guy, and this is a machining level scanner. It mounts on a stable place, and it goes around. He scanned this for me. Took him, it couldn't have been more than 20 minutes. He scanned all the way around it, and then we modeled it. And then there's the model, and that model is going to go into CD Adapco's Computational Fluid Dynamics program, and they're going to be showing some simple CFD analysis on a 1 foot footy boat that was scanned with a Faro arm, not a focus. But we can do this same thing, and we are doing this same thing with the big ships. This one, okay, that's a big one. Here's a toy. But the toy is a good example that you can actually have at the trade show, which we're going to have at SNAME for everybody to look at. Okay, so I kind of mentioned we had this docking plan. This was a vessel that was relatively new, but the hull didn't quite match the docking plan. So when they brought it into dry dock, they had to do a lot of custom location of the the dunnage. So this brings us to the purpose of scanning for a docking plan. Often ships do not have accurate hull drawings. Not every ship is built as designed. Clients have their ships scanned during dry dock so they can create accurate docking plans for the future. And if I had had the question beforehand about cleaning of vessels and then just that and painting the holes, if you've got a good hull, a model that you can give to whichever yard you're going to bring it in, they can do a docking plan and be completely prepared for that. They'll have the right amount of paint. They'll have the right manpower to clean it and prepare it. And all of that, since square footage is usually what defines the cost, it's all clean and tidy for you guys to do your estimates and for the clients to have a really good handle of their asset and what it's going to cost. So I really appreciate that question, and I think that can justify this along with all the other things that we've been talking about. So with that said, here is the Shaniga. It's a ferry up north in Alaska. Well, we get up there to scan, and we had been given the dimensions, and we had kind of estimated a 25-foot grid for scanning. Well, first thing, Daryl Sharp is our lead scanning specialist. The first thing he notices is this surface doesn't look normal. Well, they had a special treatment, coating, paint, on this that reduced friction and greatly improves the fuel economy of this. And they had just pressure washes, so it was all bright and shiny and ready to go. Well,
and dark.
And it was dark, and so the first scans spaced out were just not going to fly. So we had to basically go on an 8-foot grid and get better angles, because what would happen is a direct shot on didn't work, and too much of an angle from the scanner didn't work. It was that area kind of just outside of those two. And so, because if it's too shiny, it sends this. It basically is like a blind spot, or when you take a photo and everybody's got blue eye. It's that type of sensor back to the sensor. It's too sensitive. So we had to basically do instead of 30 scans, we did, I think it was close to 100. So fortunately, we had time, and it was right across from the airport. So when he finished, he gets on the plane and goes, and it wasn't a long wait. He couldn't have done this in Houston because he scanned right up to the minute the plane was going to leave. So I stopped the video. This rub rail, actually I should bring it back a little bit. What happens is, for the docking plan, they really care about the dimension, a reference dimension. So there had to be something that they cared about. So you'll notice we didn't model the upper part. In fact, we didn't even scan the upper part of this. We only scanned the bottom part that had to do with where the dunnage is going to go. But they did need this back rail modeled, and we had good scan data of it. And that was what everything's measured from. So next time this comes into dry dock, they will take this and run it right up to the predetermined point. They'll have all the data for what the true hole shape is, and their docking plan will match the actual docking function. So, yeah, that's some nice questions, and we are now about ready to move into the piping side of things. So, any other questions before we move into this?
There was another question, but you may have answered it. Basically, Joe said he had 2 questions. Could this be inserted and integrated into CAD/CAM drawings with this accuracy? And 2, I see the biggest and best utility for the service in terms of equipment retrofit. Is that correct?
Well, it's hard to say biggest. It just depends on what your specific needs are. And if that's your area of need, then it's huge. And with ships, it's so much more important than refineries, because you have to shoehorn everything in. You'll see in my example of a pretty tight fit of a high-pressure mud pump. They had to drop in and had 18 inches on one side. So, but you said CAD/CAM?
Yeah, could it be inserted and integrated into CAD/CAM drawings with this accuracy?
See, I'm not familiar with CAD/CAM, but if it's a standard CAD program that can take in DXF, the accuracy is very good for what we're talking about, large items. The only CAD/CAM slash function I can remember right now is machining level, like inventor type, product design stuff, and that would be your Faro arm more than the Faro focus, if that helps.
Okay, and then Martin has a question. Was the fairy paint a fluoropolymer?
I have no idea.
It was a silicone-based coating.
Okay. And then another question, would it, from Joe again, I think about the CAD/CAM, would it fit into a standard naval architect's white schematics?
I don't know. I'll try to research that and answer by SNAME. We'll have lots of naval architects around for there. In fact, most of the guys that I work with at SNAME are naval architects. So I'm not familiar with that, though. It's not something we've... It's funny. We had a lot of interest from the Navy, but everything's classified, and so we could never get past the front door, so to speak. And also, they had looked at this technology back, 10, 12 years, and it just wasn't good enough, so they didn't go any further. But they even admitted when I was interacting with them that, yeah, it's probably improved a bit. No, it's improved a lot. So I expect the Navy is self-performing. They do a lot of things that are secretive, but there's no question that it's going to become a standard part, just like digital cameras now are used to document things. You can buy a Focus 3D X330 for like $57,000. This thing shoots 330 meters, beautiful data. Every ship should have one. So.
And would you be able to elaborate on the propeller scanning and the efficiency of identifying both balance and pitch issues?
Well, we're not propeller people, but we gave the data to a propeller company, and they had a surface model of it, and it was a brass propeller, and it had a really nice data. I mean, it was really clean data. So in terms of what we would have told them it was good to, plus or minus a millimeter, they said that's more than adequate for them to determine all of that. So if you're a propeller person, we can interact with you because we know what the data is. You guys know what it actually means. Does that make sense?
It would be good to talk with someone after the webinar.
So. And actually, there will be at the end of this, we have a little how to get in contact with us. So if you're going to be at SNAME, of course, that's the best because one-on-one, and we'll have 4 guys there, and we'll have lots of opportunities to show examples of jobs in detail and such. So on to piping, obviously scope definition. It sounds nice that before you ever go to a job, that your client knows exactly what he wants you to do, but the fact of the matter is it isn't the case. So what we've actually used the scan data for is you scan the entire machining room, you create isolated data, so every pipe system is separated out to its own, so they're all in their own layers, and then they can take that model, and we've tried to get them to use it, basically a scan to plan type of format or function. Then they can say, our UT reading showed this to be thin here and here and here. Well, we're not going to just replace those 4 elbows. We're going to replace this whole line. So you can use it for scope definition. You can use it for replacing kinda. Ships are seldom, especially the older ones, are they ever laid out in a nice straight perpendicular grids. They're usually kind of stovepiped in. So typically, well, when we've done replacing kind, we've always straightened it out so that they could be prefab. You don't want to have somebody in the shop look at your drawing where it shows an 89-degree elbow instead of a 90-degree elbow. If you can fix that in your design, you want them to build what's normal, and then you want it to fit in what's normal, and you leave your field welds in such a place that you can do that. New equipment installation, ballast water treatment, Another big one is the whole exhaust gas emissions, scrubbers. Process changes, I mentioned 2 pumps where they only had one. I'll be showing one of those, and then piping upgrades. We've done some where it was a 5-inch pipe and they wanted to upgrade it to 6, same material class but larger, and they were big 5D bins, so it was a challenge. Benefits: prefabricated pipe spools. We all know it's much cheaper to build this in a shop than it is to build it in place. Increased bolt ups, flanges ready to go, reduced field welds, a significant 3D model used during planning and construction phase. This one, if you have the right construction guy, we had a job that went about as smooth as you can imagine, and it was because Carl, the guy who was running the project, he was familiar with the process. He'd been involved in another job. He believed in it. And so even when things look like they might not actually fit if you just tape measure and plumb bob, he knew from his experience that it will fit, and he had the guys just put it in. Sure enough, it fit. And we had another job where Carl was around, but it wasn't his prime job. And when he took off for a bit, they went back to the old-fashioned way of doing things, and nothing fit. Everything had to be recut and redone, and only to find out that it would have fit if they tried, but because they couldn't measure it accurately, they just assumed it wasn't going to fit. And then, of course, dry dock time, $50,000 to $80,000 a day, depending on what that is. That's reduced dry dock time. And then, of course, if you have a ship that's making money when it's on the ocean, you want it back out there, whether it's a drill ship or it's moving stuff. So all in all, a little bit of scanning investment has a huge rate of return for all of these things. And usually managers sleep better when they have been able to visualize what they're supposed to do the next day and in a 3D model. So here's a register scan data. It's a blob. A little hard to decipher what's what. You can kind of see that pipe in the bottom, but for the most part, this is not that much easier to work in when you zoom in. It's a little easier, but not a lot easier. Looks like we're getting ready to run out of time, so I'm going to zoom through these. Here's isolated scan data. This is just replacing in kind of scope defined. These were 4 engines. They were all the same, but none of the piping was the same because nothing was quite in the right place, and all this pipe had to be replaced. It was cooling water. It was at end of service life, and it just needed to be replaced. So here's a model on top of the scan data. Here's the model itself, creating the standard isometric for fabrication, spool fabrication. You'll notice here we have fabrication bill of materials and then field bill of materials. So we separate it out so it's really easy for them to manage the work. On this ship, they had 4 pumps that were just delivered, but no drawings. And they said, we need those pumps installed here because we need a spare. So we scanned the pump, and then we dropped the 2 pumps in place of where 1. So if you can see my little cursor, there was 1 pump here. Now we got 2 pumps. Well, we never even had certified drawings of the pump, but we had the pump. So we scanned the pump on the pallets, and then we used that. We never modeled the pumps. We just got those dimensions, and then we dropped them in and did the piping around it. So here's a closer shot of that. So here is the forward pump room of the Glomar Explorer. This is the color coding is isolated. The ghost image in the back is corridors. It's subsampled down to a small enough data set that you can actually use it in CAD. And then here's the new design over it. And you'll notice we actually had some lines straightened out. Before, these lines used to go around a big obstruction that was gone. So we straightened it out, and it was much easier to build, obviously. So once again, fabrication ISO.
We could also note this ship was in production about 5 months or so before it was going to the shipyard. So no downtime for the scanning.
Yeah, this was scanned while it was drilling. So this is another drill ship. This is the deck. Here's the derrick. Well, actually, this is the whole ship. So you got the scan data down below. Here we have isolated. This is the high-pressure drilling mud. So that's all we cared about was that system. We scanned it. Here's, once again, that isolated out. Then these pieces were given to the designers, and they were also given the corridors that they had to fit through, because this one we had to upsize from 5 inch to 6 inch. So all those long radius bends had to make sure they made it. And then I don't think we have time, any more time, except for a couple questions. But in a nutshell, that is our presentation. This is Cohera 3D Laser Scanning Solutions is the software company we've started, and hopefully by early next year that'll be something everybody knows. But we're just in the beginning stages of that. So, and then here's how to get a hold of us. And doesn't look like I gave you a phone number, but you can go to our website and get contact information from there. Okay, appreciate your attention. I really liked your questions. Involvement of the audience is always best.